Okay, so here we are, 5.2, Pre-Calculus 20, and in the McGraw-Hill-Ryerson Pre-Calculus 11 textbook, this is on page 282, if you're following along, and we're talking today, this lesson, about multiplying and dividing radical expressions. Okay, multiplying and dividing radical expressions. So why don't you get to this page in your textbook if you can and follow along. All right, so the intro here talks about in the early 1980s, the Voyager spacecraft first relayed messages of a special hexagonal cloud pattern in the north end of Saturn. Due to Saturn's lengthy year, so the time that Saturn takes to go around the sun, because it's so much further out, takes 26.4 of our years to go one time around the sun for Saturn. Light has not returned to its north pole until recently. The space probe Cassini has recently returned images of Saturn's north pole. Surprisingly, the hexagonal cloud feature appears to have remained in place over nearly 3 decades. Scientists are interested in the physics behind this unusual feature of Saturn. So here you see this hexagonal cloud. Okay, so what is it about hexagon? Well, hexagon has different angles and different side lengths and stuff like that. In this investigation, which we won't really do, we're going to explore the trigonometry with shapes like this. And really, even with a square, we did a question just a few minutes ago about a diagonal in a square. Okay, and when you're trying to find a diagonal in a square, you have to use Pythagoras' theorem, and sometimes you end up with a square root or a radical. Okay, so anyways, they're talking about distances between points in this cloud, and it's expressed as a radical. So this lesson is about working with radicals, specifically multiplying and dividing radicals. So this might be a little bit of a review. I'm not really sure how much you remember about this from grade 10. We talked a little bit about this in grade 10. And a little bit about this last section too. Just even in your homework you had to do this. So just a real quick reminder, when you're multiplying radicals, so for example in your textbook on this page here, which is 284, if you have two radicals that are being multiplied, you multiply the integer parts together and then separately multiply the radical parts. So root 7 times root 75 would be the same as the square root of the product, 7 times 75. Now when you get to this point, you've multiplied those, and they're still kind of separate. They're multiplied, but they're separate. You might have to simplify the radical part. So root 525 has a perfect square factor of 25. So you have to simplify that like you would anything else. Okay? Now if you want, you could simplify, and this is an alternate way of doing it. You could simplify the radical first, and then you have a better chance of not having to simplify later. So if you want to simplify root 75 first, you can do that. It might be a little bit easier to find a perfect square factor of a smaller number. So you might want to do that first. Either way, you should get the exact same answer when you're all done. So if you see something highlighted in blue in your textbook, it's probably a summary or an important part of what they're trying to teach you. So in general, if you have two radicals, and they've substituted letters for the parts of the radical. So if you have two radicals, you can multiply the integer parts, that is the number parts in front, and just write that as a product, and then times the product of the radical parts. And that is if this index, the k part, is the same for both. If you have a square root and a cube root, this doesn't apply. Okay? So you got to think about that just a bit differently. Okay? Now, here's some examples. Here, I'm going to let you just take a look at these. It's exactly what we've said. In B, you have to distribute. Okay? You have to distribute just like you normally would with any other numbers or expressions. This term here multiplied by the first term, and then multiplied by the second term, and then you combine those if you can. So we'll do some examples here. They should have a your turn. That would be good for us to do. Yeah. Let's tackle some of these questions here, multiplying. Okay. So write these examples down in your book, and let's go through them together. So hopefully this is easy for you. I'm not really sure if it's easy for you or not, but let's just give it a try. So if we're asked to multiply these two things together, 5 root 3 and root 6, that's really the same as, like 5 root 3 is just 5 root 3, but this is the same as 1 root 6, right? So just so long as you guys know that, if there's nothing shown there, that's a 1. So we do 5 times 1, and then square root of 3 times 6. Multiply the integer parts, and multiply the radical parts. These are both square roots, so we're good to go. This is 5 root what? 18. Now, root 18, can that be simplified? Because we should simplify. So factors of 18, is there a factor that's a perfect square? Yep, 9. So guess what? This is 5. Now I can pull that 9 out right away. I can start showing less work if you're understanding this now. I'll write it anyways. Root 9 times root 2. So this is 5 times 3 root 2, or 15 root 2. Make sense? Okay. What about C? Let's take a look at C. So C is, and I'll rewrite it here, 4 root 2 plus 3. We have a binomial times another binomial. Okay. When you multiply binomials, remember you have to distribute twice, or the FOIL method. Some of you like the FOIL method, remembering that. And the FOIL method, of course, is multiplying the first terms together. That's the F in FOIL. And so 4 root 2 times root 7 is what? Anybody brave enough to shout it out there? 4 root what? 14. Yep. So 4 times 1, root 2 times 7. Good. The outside terms go next. That's the O in FOIL. So we have 4 times 5, or negative 5. Remember the sign here. So that's minus 20 root. Well, 14 times 2 is 28. Okay. Now let's go to the inside terms. So that's what the I stands for. So we've got 3 times root 7. So that's plus 3 root 7. And then L is last terms. So 3 times 5 root 14. It's a negative 5, so it's minus 15 root 14. Okay, so that's your first step of FOIL. A couple other things we need to do. We need to gather like terms if we can, and we need to simplify if we can. So I see some like terms here, so you could simplify those right away if you like doing that right away. So 4 root 14 minus 15 root 14. 4 minus 15 is negative 11 root 14. Okay, those are taken care of. What do you notice with these two terms? Anything jump out at you? What do you notice with those two? Are they like terms? No, yes? Okay. What you want to notice here is that root 28 should be able to be simplified because it has a factor of 4, right? 4 times 7. So this is actually minus 20 times root 4 times root 7. So when you said no, they're not like terms, and then you said yes, they are like terms, you're right, they are like terms. So let's do that. So this is actually 20 times 2, right? That root 4 is a 2. So 20 times 2 is negative 40 root 7 plus 3 root 7. Are we good with that? So now these are like terms, so we just combine the front. So we have negative 11 root 14 minus 37 root 7. And those are unlike terms, they can't be simplified. And then we're done. Okay, any questions on that? All right, so this example here, if we're talking now about dividing radicals, if you have a division of two monomial radicals, how do you go about that? Well, the rules are really much the same as multiplying. So when you are multiplying, you take the integer parts and multiply them together, and then the radical parts and multiply them together, as long as the index is the same. So with dividing, it's very similar. You just take the number parts and you simplify those. Divide them if you can, or write them in simplest fraction form. And then you do the same thing with the numbers underneath the radical sign. So this is equal to 12 divided by 3 times cube root, and I'll just write it. I'll write it like this so you can kind of see. Cube root of 21 divided by 7. So you just divide those parts. And if you can combine them, simplify them, that's great. So this is 4 times the cube root of what? 3. Okay, 4 times the cube root of 3. And you don't have to trust me, I guess, if you don't want to. We could check it out. So let's try it. 12. Now, do I have a cube root button? I think I do. 12, yeah, here we go. Cube root of 3 divided by 3 cube root 7. I might need to insert a bracket there. Just give me a second. Insert a bracket here. Make sure we got everything covered. Okay, that should work. Okay, so 3.01. And let's test out the simplified version then. So 4 times the cube root of 3. That didn't work, did it? What did I do something wrong here? Oh yeah, sorry. This other one. I don't know if I can get to it now. Let me see. Thank you. Whoops. Entry. Can I get to the other entry? Oh, there we go. Thank you for noticing that. This should be a 21. I'll delete that. Okay, there we go. And 5.76. So yeah, thank you. So you got 21 in there, not 3, and 5.76899, and the simplified one is also 5.76899. Okay? Thank you for noticing that. So anyways, all that to say that this simplification, seems to be verified there. All right? Any questions? So I'll just highlight this blue section again, dividing radicals. Yeah, divide the integer parts and divide the radical parts as long as the index of the radicals are the same. Okay, so this is a big part of this lesson. This is probably something that would be fairly new to you. And we're talking about rationalizing specifically the denominators. So you guys hopefully have seen this before, but let's focus on it right now. If we want to rationalize a denominator, that means we want to make the denominator rational. So if it's irrational, for example, this is an example, 5 over 2 root 3, there's a radical in the denominator. So in order for this to be simplified, really, technically, there shouldn't be a radical in the denominator. So how we do that is we multiply both the top and the bottom of the fraction, or the rational, by the radical part that we see in the denominator there. Okay? And so that's what you see is done here. Now what does that do? Well, it makes the radical part in the denominator, it squares it. And so that gets rid of the radical part. So root 3 times root 3 is just 3. So you have 2 times 3, and that's what you have in the bottom. Now it does make the numerator irrational, but we want the denominator to be rational, so that's what we do. Now if we have something like this, okay, I'm just going to clip this out as the example. If we have a denominator that is not a single term, and we want to rationalize that, so just jot this down here, that example. And that's going to be rationalizing denominator. Okay, so if we have this as an example, and this is a binomial in the denominator. So if we did this, if we said, well, I know how to get rid of a radical in the denominator, I just multiply top and bottom by the radical part. So if you did that, this is what would happen. You'd have 5 root 18, and you'd have, well, this would now have to be distributed. So you'd have 4 root 6 minus 6. So this is not enough to rationalize the denominator when the denominator is a binomial. So what do we do? Well, what we do is this. You take that denominator, and you have to multiply it by its conjugate, okay? The conjugate. Apologize for the messy writing, but that says C-O-N-J-U-G-A-T-E, the conjugate. So if we go back to the text, the conjugate is simply, well, you see an example down here. It's the same terms in a binomial, but the opposite sign in between. The same terms, but the opposite sign. Now, what does this give us? This gives us a situation where if we were to multiply those two, we get what's called a difference of squares. Remember that? So if you get a difference of squares, that means that each term is actually squared, and that eliminates a square root. So let me show you. What you do here is you say, okay, I'm going to multiply the top and the bottom by the conjugate of this binomial. So that's going to be 4 plus root 6 on the bottom and the top. Of course, we don't want to change the nature of the rational, so we have to do the same thing to the top and bottom. So when we do that, this has to distribute. So that's going to be 20 root 3. So 5 root 3 times 4. And then plus 5 times 1, that's 5 root 18. 6 times 3. And this isn't simplified, I know that, but let's see what happens on the bottom. Well, when we do this now, a binomial times a binomial, we get 16 plus 4 root 6 minus 4 root 6 minus root 6 squared, or just 6. So this is in effect how we eliminate the radicals. We multiply by the conjugate because look at positive 4 root 6 and negative 4 root 6 completely cancel each other out. So now we probably should simplify this up at the top there. So let's do that in this step. Root 18 has 9 as a factor. So root 9 comes out as a 3, right? So if a factor in there wants to get out of the root club, then getting out, it has to get square rooted. So this is plus 5 times 3, or 15 root 2. Okay? And then over here we have 16 minus 6. So that's 20 root 3 plus 15 root 2 over 10. And we can't combine these because they're unlike radicals. We could do some factoring. Yes, we could do some factoring and simplifying. So I think if we're going to simplify this, write down, we could divide 5, I guess, out of all of these, right? So you could divide every term by 5. And that would reduce that. So that would be 4 root 3 plus 3 root 2 over 10 over 5 is 2. So that's your simplified version. All right. Questions? I know this stuff is really exciting. Okay? Not my fault. It's something you have to do. So if this is old news to you, great. If this was easy and you're like, I remember all this stuff, I've done this before, whatever, that's great. If not, then here's your time to practice this, okay? So back to the textbook here. Let's see. There's some examples I'll get you to look through. All right. And but we're coming to the end here. So this is the key ideas. Please take a moment to read through the key ideas. And then I'll give you your assignment. Well, where'd they go? Okay. Here's your assignment from 5.2.
Yeah, I don't know.